Welcome back to our lecture series on nanostructural materials, science and technology. I am Professor Ashutosh Tiwari from the Department of Material Science and Engineering at the University of Utah. In the previous lecture, we explored top-down nanofabrication, methods that start with bulk materials and sculpt them down to the nanoscale using mechanical patterning or etching processes. Today, we shift to complementary viewpoint, bottom-up nanofabrication, where structures are built atom by atom or molecule by molecule, guided by chemistry, thermodynamics, and the natural tendency of materials to organize themselves into ordered patterns. This approach lies at the heart of modern nanoscience, from the self-assembly of DNA and block copolymers to chemical and vapor phase synthesis of nanoparticles, nanowires, and thin films. By the end of this lecture, you will understand how bottom-up methods achieve atomic scale control, enable uniform growth of nanostructures, and often provide a simpler, energy-efficient route to producing materials with remarkable precision. Let us begin by contrasting bottom-up and top-down approaches of fabrication to see how each contribute to creation of nanostructural materials. Bottom-up nanofabrication is fundamentally different from top-down. Instead of carving down bulk material, we build structures atom by atom or molecule by molecule. The process is guided by chemistry and thermodynamics, allowing systems to organize themselves into stable configurations. It does not replace top-down. Rather, the two approaches complement each other. For example, top-down lithography can define large-scale patterns, while bottom-up assembly can fill in the nanoscale details. Together, they enable structures beyond the resolution and cost limits of conventional lithography. Bottom-up nanofabrication is governed by a set of universal principles. At the foundation lies chemistry and thermodynamics, which control how atoms and molecules bond, nucleate, and grow. Structures evolve by minimizing surface and interfacial energy, which is why nanosystems tend to form ordered states like crystals, micelles, or nanowires. Finally, through self-organization, matter arranges into stable patterns without external intervention, producing order from simple local rules. Nature has been practicing bottom-up nanofabrication for billions of years. DNA molecules self-assemble into the iconic double helix through complementary base pairing. Proteins fold into precise three-dimensional structures dictated by amino acid sequences, achieving extraordinary functions like catalysis and transport. Virus capsids are striking examples of self-assembly. Hundreds of protein subunits spontaneously arrange into symmetric shells that protect genetic material. These natural systems remind us that bottom-up strategies are not just possible but incredibly powerful, inspiring many of the approaches we adopt in nanotechnology today. Self-assembly allows atoms, molecules, or nanoparticles to organize themselves into ordered structures by reaching equilibrium states. The process is spontaneous, but not random. Conditions such as solvent type, acidity or pH, and temperature strongly influence the outcome. By carefully controlling the environment, we can guide self-assembly toward specific morphology, whether that is spherical micelles, lamellar domains, or three-dimensional colloidal crystals. This makes self-assembly one of the most versatile and scalable bottom-up nanofabrication tools. Several fundamental forces drive self-assembly and bottom-up nanofabrication. First is the surface energy. Atoms and molecules arrange to minimize high-energy interfaces leading to phenomena like micelle formation and thin film growth. Electrostatics govern attraction and repulsion between charged species, strongly influencing colloidal stability. Hydrogen bonding provides directional stabilization, critical in DNA base pairing and protein folding. Finally, van der Waals interactions, though individually weak, are universal and collectively significant in holding molecular assemblies together. The interplay of these forces explains why nanoscale systems spontaneously form ordered structures. Colloidal self-assembly is one of the most striking demonstrations of bottom-up nanofabrication. Spherical colloidal particles suspended in a solution can spontaneously organize into ordered three-dimensional lattices. These periodic arrays, known as photonic crystals, have the ability to manipulate light much like semiconductors manipulate electrons. A beautiful natural example is the gemstone opal, which derives its iridescent colors from the ordered arrangement of silica nanospheres acting as a photonic crystal. In the lab, scientists mimic this principle to fabricate photonic materials for lasers, sensors, and displays. Block copolymers consist of two or more polymer chains covalently bonded together, but chemically incompatible. Because the blocks cannot fully separate like oil and water, they undergo microphase separation instead. This results in ordered nanoscale domains such as lamellae, cylinders, and more complex structures like gyroids. What makes block copolymer self-assembly especially valuable is the scale. Domain sizes are typically only 10 to 50 nanometers, far smaller than what can be achieved using conventional photolithography. As a result, block copolymers are increasingly explored as templates for nanopatterning in semiconductors and nanomanufacturing industries. In many self-assembly systems, order can be limited by defects or grain boundaries. To overcome this, we use templated self-assembly, where a substrate pattern directs the organization of block copolymer or colloids. In graphoepitaxy, surface topography such as shallow trenches or groups provides physical guidance, forcing domains to align. In chemoepitaxy, chemical patterns like alternating hydrophobic and hydrophilic strips induce selective wetting of polymer blocks, leading to defect-free registration. Templated self-assembly combines the precision of lithography with the nanoscale resolution of bottom-up methods. Like in crystals, self-assembled nanostructures are never perfectly ordered. Defects are inevitable. These defects can include dislocations, grain boundaries, or vacancies in colloidal or polymer assemblies. While defects often disrupt long-range order, they are not always harmful. In fact, defects can be harnessed for specific functions. For example, defect engineering in nanocatalysts creates active sites that enhance reactivity. Similarly, control disorder in photonic crystals can improve light scattering for sensing application. So, rather than eliminating defects entirely, nanofabrication often seeks to control and exploit them. Self-assembly is the bridge between chemistry and nanotechnology. It transforms simple molecular interactions into functional nanoscale architectures. At its core, this process allows atoms, molecules, and nanoparticles to spontaneously organize into ordered structures with precisely controlled optical, electronic, and surface properties. Instead of carving patterns as in top-down methods, self-assembly lets materials build themselves through thermodynamic and chemical guidance. These principles underpin a wide range of technologies. Ordered nanoparticle arrays enable ultra-dense data storage. Periodic nanostructures form photonic materials that control light, and patterned molecular films create templates for sensors and electronic surfaces. Together, they illustrate how self-assembly converts fundamental chemistry into practical nanotechnology, offering an elegant, efficient route to functional devices. Self-assembly shows us how molecules and particles naturally organized, but we can go further using chemical synthesis in solution to deliberately control particle size, shape, and composition. One of the most widely used approaches in bottom-up nanofabrication is solution chemistry. Nanoparticles can be synthesized in simple beakers or more controlled chemical reactors. The key advantage of solution phase methods is the ability to tune particle size, shape, and even composition by adjusting reaction conditions such as temperature, concentration, and solvent. Surfactants and organic ligands play a critical role here. They selectively bind to certain crystal facets, slowing growth in one direction and enabling control over whether the product is spherical, rod-like, or plate-like. Because solution chemistry is scalable, it is an industrially important method for producing nanomaterials. Next, we will look at some of the most common chemical routes in more detail, such as sol-gel and hydrothermal methods. One of the most versatile chemical synthesis routes is the sol-gel method. It begins with a solution of metal alkoxide or metal salt precursors. Through hydrolysis and condensation reactions, a colloidal suspension known as a sol forms. As the process continues, these nanoparticles interconnect into a continuous 3D network called a gel. After drying and calcination, the gel is transformed into metal oxides such as silica or titanium. This technique is highly flexible. It can produce nanoparticles, thin films, fibers, or porous bulk materials simply by varying how the gel is processed. Because of its chemical versatility and relatively low processing temperatures, the sol-gel route is widely used in coatings, optics, and catalysis. Another powerful solution-based synthesis route is the hydrothermal or solvothermal method. In this approach, precursors are dissolved in water or another solvent and heated in a seated autoclave at high temperatures and pressure. The enclosed environment promotes controlled nucleation and slow crystal growth, leading to highly crystalline products. By adjusting reaction parameters such as temperature, time, and solvent type, we can selectively produce nanowires, nanorods, or nanotubes. This method is particularly useful for synthesizing oxides, sulfides, and other inorganic nanomaterials with well-defined shapes and high crystallinity. It is widely applied in photocatalysts, energy storage, and nano devices. Two related chemical routes for nanoparticle synthesis are polyol method and microemulsion method. In the polyol method, solvents such as ethylene glycol act not only as a medium but also as a reducing agent. This allows the direct synthesis of uniform metal nanoparticles such as silver, platinum, or copper, often with controlled shapes. The microemulsion method, on the other hand, uses water in oil or oil in water systems, where nanodroplets act as tiny nanoreactors. The size of these droplets controls the size of resulting nanoparticles, leading to excellent monodispersity. Both approaches are highly tunable and are widely used in producing functional nanoparticles for catalysis, electronics, and biomedical applications. Let us look at a specific case study, quantum dot synthesis. Quantum dots are semiconductor nanocrystals with common examples including cadmium selenide, CdSe, and lead sulfide, PBS. What makes them unique is their size-dependent optical band gap, a direct result of quantum confinement. As the crystal size decreases, the band gap widens, shifting emission toward the blue. Larger dots emit toward the red. This tunability makes quantum dots extremely attractive for applications ranging from quantum dot displays and LEDs to solar energy harvesting to fluorescent markers in biological imaging. Controlled synthesis using hot injection or colloidal methods allows precise tailoring of size, shape, and surface chemistry to achieve these properties. Another cornerstone of bottom-up nanofabrication is chemical vapor deposition or CVD. In this method, volatile chemical precursors are introduced in the gas phase and transported to a heated substrate. There, they undergo chemical reactions that deposit thin films or nanostructures. CVD is highly versatile. It can produce conformal coatings, semiconductor thin films, or even complex nanostructures such as carbon nanotubes and graphene. Because it delivers excellent control over thickness, composition, and crystallinity, CVD is one of the most widely used methods in microelectronics, photovoltaic, and energy storage technologies. Atomic layer deposition or ALD is one of the most precise bottom-up fabrication methods. It relies on self-limiting surface reactions, meaning that only one atomic layer can form during each reaction cycle. By alternating precursor pulses, material is built up layer by layer. Because of this mechanism, ALD provides angstrom level thickness control, far more precise than conventional thin film methods. Another unique advantage is that ALD produces highly conformal coatings, even over rough, porous or three-dimensional surfaces, such as nanopores, nanotubes, or complex device geometries. This makes it indispensable for microelectronics, protective coatings, and energy storage devices like lithium-ion batteries. Another widely used bottom-up nanofabrication route is vapor-liquid-solid growth or VLS. In this method, a metal catalyst droplet such as gold is placed on a substrate. Vapor phase precursors like silicon containing gases dissolve into the droplet. As the droplet becomes supersaturated with the precursor, the solid material precipitates out at the liquid-solid interface, causing a nanowire to grow upward beneath the droplet. This mechanism allows controlled synthesis of semiconductor nanowires with the catalyst droplet typically sitting at the tip of the nanowire during growth. A classic example is the synthesis of silicon nanowires using gold catalysts, which has been a model system for nanowire growth and device fabrication. Two-dimensional materials like molybdenum disulfide and tungsten disulfide represent another exciting case study in bottom-up nanofabrication. These layered semiconductors are often synthesized using CVD growth, which enables large area atomically thin sheets. Because they are only a few atoms thick, these materials exhibit a strong quantum confinement, direct band gaps, and remarkable electronic and optical properties. MOS2 and WS2 are being actively explored for field effect transistors, photoretectors, and flexible optoelectronic devices. Their combination of high carrier mobility, tunable band gaps, and mechanical flexibility makes them promising for next generation nanoelectronics. While CVD and ALD offer excellent thin film growth, some applications demand even greater purity and atomic level control. This is where molecular beam epitaxy or MBE comes in, enabling monolayer growth with ultra-clean interfaces. MBE takes place in ultra-high vacuum chamber where atomic or molecular beams of source materials are directed toward a heated substrate. Because the environment is so clean and deposition rates are deliberately very low, MBE allows monolayer by monolayer control of film thickness. This precision enables the fabrication of ultra-pure interfaces and heterostructures, making MBE indispensable in advanced electronics, optoelectronics, and quantum device research. One of the landmark achievements of molecular beam epitaxy is the creation of quantum wells and superlattices. In a quantum well, a thin semiconductor layer, such as gallium arsenide, is sandwiched between higher bandgap barriers like aluminum gallium arsenide, confining electrons and holes in 2 dimensions. By stacking these wells periodically, we can create superlattice with tailored electronic and optical properties. Because MBE allows monolayer control, it makes possible the precise engineering of band structures, something not achievable with traditional deposition methods. These structures revolutionize optoelectronics, leading to modern laser diodes, infrared detectors, and optical modulators that are ubiquitous in today's communication and sensing technologies. Both MBE and CVD are powerful bottom-up thin film growth techniques, but they serve different needs. MBE offers unmatched precision and purity, operating in ultra-high vacuum with monolayer level control. This makes it indispensable for fundamental research and specialized heterostructures like quantum wells. However, its deposition rate is very slow and scalability is limited. CVD, on the other hand, is much more scalable, widely used in industry for large area thin films, nanotubes, and graphene. It offers good control, but not at the atomic level precision of MBE. In short, the trade-off is precision versus scalability, and the choice depends on the application. So far, we have explored chemical vapor deposition and atomic layer deposition, which rely on chemical reactions at the surface, and then molecular beam epitaxy, which provides atomic scale precision. Now, there is another broad class of methods known as physical vapor deposition, or PVD. In these techniques, atoms are physically transported in vacuum from a source to a substrate to form thin films. You can think of MBE as a very specialized form of PVD, operating in ultra-high vacuum with monolayer control. But it is often discussed separately because of its unique role in epitaxial heterostructures. The general PVD methods we will focus on are evaporation, sputtering, and pulse laser deposition, PLD. These approaches are versatile and widely used in research and industry, from depositing semiconductor layers to optical coatings on lenses and even hard coatings on tools. Among physical vapor deposition methods, thermal evaporation is the simplest and most widely used. In this technique, the source material is heated resistively in a crucible until it vaporizes, and the vapor then condenses on the substrate to form a thin film. A more advanced variant is electron beam evaporation, or E-beam evaporation, where a focused high-energy electron beam is used to melt and vaporize the source material. This allows evaporation of materials with much higher melting points and provides better control. Both methods are straightforward and effective, making them common choices for depositing metallic thin films in research labs and small-scale applications. However, they also have important limitations. Because the vapor travels in line of sight, these methods suffer from poor step coverage on complex 3D structures. In addition, it can be difficult to maintain the exact stoichiometry of compounds since different elements may evaporate at different rates. Despite these limitations, evaporation remains one of the most accessible and versatile PVD techniques. Another major PVD technique is sputtering, which uses a plasma to bombard a solid target with energetic ions. These ions eject atoms from the target, which then travel through vacuum and deposit onto a substrate, forming a thin film. There are several modes of sputtering. DC sputtering is typically used for conductive targets like metals, while RF sputtering allows deposition from insulating targets such as oxides. A further improvement is magnetron sputtering, which uses magnetic fields to trap electrons near the target surface, increasing plasma density and improving deposition rate. Sputtering is one of the most versatile thin film deposition techniques. It is widely used to make metallic coatings, oxide films, and multi-layer structures, ranging from optical coatings to magnetic storage media. Another important physical vapor deposition method is pulse laser deposition, or PLD. In PLD, a high-energy pulse laser is focused onto a solid target in vacuum. The laser energy rapidly heats and vaporizes a small spot on the target, producing a highly energetic plasma plume that expands towards the substrate. A key advantage of PLD is stoichiometric transfer. The composition of the complex targets, such as oxides or superconductors, is often preserved in the deposited thin films. This makes PLD especially valuable for growing multi-component materials that are difficult to synthesize by evaporation or sputtering. PLD has become a powerful research tool for preparing thin films of oxides, high-temperature superconductors, and even emerging 2D materials like molybdenum disulfide. Soft lithography is a versatile bottom-up nanofabrication technique that uses elastomeric stamps or molds, typically made from PDMS to create patterns. Unlike conventional photolithography, which requires expensive optics and masks, soft lithography is flexible, inexpensive, and adaptable. The basic idea is to cast a soft polymer like PDMS against a master template, then use it as a stamp or mold to transfer features onto another surface. This approach is practically useful for fabricating microfluidic devices, biosensors, and nanopattern surfaces, making it a key tool in both research and applied nanotechnology. Microcontact printing is a soft lithography technique where a PDMS stamp is inked with molecules, often thiols or biomolecules, and then pressed against the substrate. The molecules transfer to the surface, forming self-assembled monolayers in the stamp pattern. This approach allows controlled biomolecule patterning for biosensors, cell adhesion studies, and chemical templating. It is widely used because it is inexpensive, straightforward, and effective at both micro and macro scales. Another important soft lithography technique is Nanoimprint lithography. Instead of using light or chemical self-assembly, Nanoimprint relies on physically pressing a hard mold into a resist layer on a substrate. After curing, the resist retains the nanoscale feature of the mold. This technique can achieve sub-10 nanometer resolution, rivaling electron beam lithography, but at a fraction of the cost. Because it is both low cost and high throughput, Nanoimprint lithography is widely used in fields like data storage, photonics, and flexible electronics. Soft lithography has found wide applications across science and engineering. One of the most important is in microfluidics, where patterned channels and valves allow precise manipulation of fluids at the micrometer scale. This underpins technologies like droplet generation, point-of-care diagnostic, and cell sorting. Another key application is in flexible electronics, where conductive patterns can be printed onto bendable substrate, enabling wearable devices, stretchable sensors, and foldable displays. Finally, soft lithography powers lab-on-chip systems, which integrate chemical or biological analysis into miniaturized devices. These platforms allow rapid diagnostics, high throughput screening, and portable biomedical tools. Together, these examples highlight the versatility and impact of soft lithography. Up to this point, we have looked at fabrication tools and techniques. But to truly understand why nanostructures form the way they do, we need to look deeper into thermodynamic principles that govern their morphology. Growth is controlled by the balance of surface free energy of the substrate, sigma S, the film, sigma F, and the substrate film interface energy, sigma SF. Depending upon these relationships, three distinct modes emerge. In the Frank van der Merwe growth mode, when the substrate surface energy is greater than the sum of the film and interfacial energies, that is, sigma S is greater than sigma F plus sigma SF, atoms spread uniformly across the substrate. This produces smooth layer by layer films. In the Warmer-Weber mode, when the substrate surface energy is smaller, that is, sigma S is less than sigma F plus sigma SF, atoms cluster together instead of wetting the surface, leading to island growth. This is how quantum dots or nanoparticles often form. In the Stransky-Krasnov mode, growth begins layer by layer, but strain accumulation makes the system switch to island formation after a few layers. This hybrid pathway produces islands on top of thin films, common in self-assembled quantum dot growth. By controlling these energy balances, we can direct whether a system grows dots, wires, or ultra-thin films, tailoring structures for different applications. So far, we have looked at how thermodynamics governs nanostructure morphology, but in real synthesis, kinetics and thermodynamics compete to determine the final structure. Under kinetic control, conditions such as rapid quenching, fast nucleation, or short reaction times freeze the system into metastable states. This often leads to smaller nanoparticles or unusual shapes that are not the equilibrium form. In contrast, under thermodynamic control, the system has enough time or energy through slow growth, annealing, or long reaction times to relax into the lowest energy state. This usually produces more uniform, faceted nanoparticles that minimize surface free energy. A classic example is nanoparticle size control. Rapid quenching can trap many small particles, while slow annealing favors fewer, larger, and more stable particles. Thus, the balance between kinetics and thermodynamics provides a powerful handle for tailoring nanostructural properties. In this lecture, we explore the essential ideas of bottom-up nanofabrication, the counterpart to the top-down approaches we studied earlier. Here, instead of carving or patterning bulk materials, structures are created atom by atom or molecule by molecule, guided by chemistry, thermodynamics, and surface energy minimization. We begin with the principles of self-organization, drawing inspiration from natural systems such as DNA, proteins, and colloidal crystals. We then examine how these same driving forces are harnessed in self-assembly, solution-based synthesis, and vapor phase deposition. Techniques such as sol-gel processing, hydrothermal growth, chemical and atomic layer deposition, and molecular beam epitaxy enable precise control of structure and composition at the nanometer scale. We also discussed how soft lithography extends these ideas to flexible patterning and how the thermodynamic and kinetic balance during growth determines whether material forms smooth films, islands, or hybrid nanostructures. Together, these methods show that bottom-up fabrication offers a powerful and energy-efficient route to produce nanomaterials with atomic level precision, tunable size and shape, and broad applicability in electronic, photonics, and catalysis. Combined with top-down approaches, they complete the toolbox of nanotechnology, bridging the gap between molecular design and functional nanoscale systems.